Hi everybody, this is the last video lecture of the semester and we're going to be looking at grafting. Before any grafting can take place, the plants that are going to be grafted have to be produced, and they're produced using several of the techniques we've looked at over the course of the semester, such as growing from seed, cuttings, layering and tissue culture. And that's why I always leave grafting till last. I want you to be familiar with all of those other techniques first. By the end of this unit, you'll be able to define grafting, describe the main applications and benefits of grafting, and describe the types of plants that grafting techniques are used for. Let's start by looking at what grafting is. Grafting isn't new. Budding and grafting techniques have been used for over 3,000 years. Old manuscripts show us that the ancient Chinese practiced the art of grafting, as did the ancient Greeks. Some of you may have seen naturally occurring grafts, where two adjacent intact plants or different branches of the same plant graft themselves together and function as one. Intentional grafting by humans involves inserting a single bud or a stem with several buds cut from one plant into an opening cut in another plant that is or will be growing on its own root system. A good formal definition of grafting was provided in a review of the history of grafting by Dr. Ken Mudge from Cornell University and his associates. They defined grafting as the natural or deliberate fusion of plant parts so that vascular continuity is established between them, and the resulting genetically composite organism functions as a single plant. Let's start by just showing you a quick video of what grafting is. In this short video, you can see Rosario at Four Winds Growers in Watsonville grafting a Swanhill olive scion onto a Frantoio olive rootstock. The rootstock was grown from cuttings and is already fully rooted into a 2-inch pot. The scion wood was collected from plants in the nursery, and the technique that Rosario's using is a whip graft. You saw her making 2 matching cuts in the top of the rootstock and the bottom of the scion, and then finishing up by taping them together with grafting bands. Before talking more about grafting, it helps to know some of the terminology. In its most basic form, a grafted plant consists of 2 parts from 2 completely different plants. A lower part with roots and an upper part that has branches or stems. The terms rootstock, stock, or understock all mean the same thing and refer to the lower or lowest portion of the grafted plant. The rootstock can be grown from seed, cuttings, layering, or tissue culture. The term scion refers to the shoot that's cut from the appropriate donor plant that will grow into the upper portion of the grafted plant. It usually consists of a length of stem containing at least 1 dormant bud. Budding refers to several grafting techniques where the scion consists of usually just a single bud, as opposed to several buds on a length of stem. As with all methods of propagation, hygiene is important in grafting, and the scion or budwood and rootstock should all be free from any known pests and diseases. Sometimes a third piece of stem is used between the rootstock and scion and is referred to as the interstock. It's also called an intermediate stock or an interstem. Grafting techniques that use an interstock are referred to as double working because you have to do 2 grafts, one joining the interstock to the rootstock and a second one joining the interstock to the scion. There are several reasons why an interstock may be used. Firstly, there may be incompatibility problems between the scion and the rootstock, and using an interstock from a third plant may help to overcome this. Secondly, the interstock may be used to confer additional characteristics on the grafted plant that aren't possessed by either the rootstock or the scion. For example, it might confer disease resistance or cold hardiness. Let's look now at where the scions, rootstocks, and interstocks all come from. Rootstocks are grown using several of the propagation methods that we've discussed in earlier modules, from seed, cuttings, layering, or tissue culture. Seedling rootstocks are cheaper than rootstocks produced by vegetative methods because there's usually less labor involved. Seedling rootstocks of some species may be preferred by some growers. For example, they may have stronger root systems than vegetatively produced rootstocks. Many citrus varieties are produced from seedling rootstocks. For example, Four Winds growers in Watsonville, which is a specialty citrus nursery, buys in citrus seed from the specialty seed producer Lynn Citrus Seed in the San Joaquin Valley. Seed may not always be an appropriate production method for growing rootstocks, though. For example, many rootstocks are hybrids or named selections of a species, so they won't come true from seed. For these rootstocks, vegetative propagation methods have to be used. One example is the Swan Hill olive, which is a fruitless olive tree used for ornamental landscapes, and it's usually grafted onto rootstocks of the named olive varieties Mission or Frantoio, which are grown from cuttings. Gisela rootstocks used for cherry are also grown from cuttings, and you can see a photo of these on the right at Carlton Nurseries in Oregon. I mentioned just now that Four Winds growers in Watsonville grow their citrus rootstocks from seed. Well, once the seedlings are large enough, they prune them back before they're grafted, and they then use the prunings as cuttings to produce more rootstocks, so that none of the material is wasted. There are some hybrid or named selection rootstocks that are really hard to root from cuttings, and are produced by a method of vegetative propagation called mound layering or stooling. Some rootstocks of apple, pear, and cherry are produced using this method. Rootstocks aren't usually grown this way in California, though, because freely draining sandy soils are needed, so much of the production is done in Oregon, in the US. Rooted rootstocks are harvested during the dormant season, stored in coolers, and sold to growers across the country. Lastly, an increasing number of rootstocks are being produced from tissue culture. In the module on tissue culture, you saw photos of plug trays of young prunus rootpack rootstocks, which are used for almond trees, being hardened off in tents at North American plants in Oregon. Several of the nut and stone fruit nurseries in California's Central Valley are now growing rootstocks in their own tissue culture labs, and Birchall Nursery in Oakdale and Duarte Nursery near Modesto are two examples of this. So where does the scion wood come from? The scion wood comes from existing plants. There are specialist nurseries that sell scion wood, and they usually have fields of stock plants that are hedged or pruned in ways that encourage production of a lot of vegetative stems that scion wood can be collected from at the appropriate time of year. For winter deciduous fruit trees, the appropriate time of year is usually in the winter, after the trees have lost all their leaves. For commercial orchards and growers, it's important that scion wood be free of disease. So scion wood can also be obtained through the National Clean Plant Network. This is a nationwide voluntary association of specialty crop networks that have joined together to promote the use of pathogen-tested, healthy plant material for economically important specialty crops in the US. Crops included in the network include berries, fruit trees, almonds, citrus, grapes, hops, roses, and sweet potatoes. For home orchards in California, small numbers of scion wood can be obtained at the California Rare Fruit Growers Scion Exchanges, which are a great source of more unusual varieties, as well as a fabulous source of information. Our local Monterey Bay chapter of the California Rare Fruit Growers holds their scion exchange at Cabrillo in January every year, and usually does grafting demos too. It's really important for you to note that by law, all seed, scion, and rootstock wood for all types of citrus must come from a source that's registered with the Citrus Nursery Stock Pest Cleanliness Program. You now know a little about what a scion and a rootstock are. Let's talk about what the requirements are for a scion and rootstock to grow together as a successful grafted plant. Firstly, it's important to know that not all plants can be grafted. Monocots can't be grafted because they don't have vascular cambium. Vascular cambium is an area of meristematic growth in dicots, where in a graft, the cells divide and differentiate to form callus and to form new vascular connections between the rootstock and scion, which of course are necessary for the plant to function as a single unit. So the rootstock and scion have to be compatible in order for the graft to take. The more closely related the plants are that the scion and rootstock come from, the more likely they are to be compatible. This concept is illustrated in the compatibility pyramid diagram on the right, where you can see that the graft is likely to be very successful within a species and becomes less and less likely to be successful as the scion and rootstock become more distantly related. There are many interspecific grafts, and there are a few, but not very many, intergeneric grafts. There are no successful grafts that have been made between a scion and rootstock from different families. Examples of interspecific grafts include the use of California walnut, Juglans heinzii, as a rootstock for English walnut, Juglans regia. Horned melon, Cucumis metuliferus, is used for cucumber, which is Cucumis sativus, and Citrus trifoliata and Citrus macrophylla are used for many citrus varieties. An example of an intergeneric graft is pear, which is a pyrus, which is grafted onto quince rootstocks, which is Cydonia oblonga. Sometimes a graft may take and then the incompatibility may not show up for several years. Signs that a graft combination is incompatible include a high proportion of grafts failing to form a union, poor vigor in the grafted plants, yellowing foliage, early defoliation, shoot dieback, and uneven growth in the diameters of the rootstock and scion. Sometimes the scion and rootstock will just break apart. For commercial growers, it's obviously really important to select rootstock and scion combinations that have been well tested. When the rootstock and scion are placed together to form the graft, it's important that the vascular tissue of the rootstock and scion, and interstock if one's used, line up as shown in the diagram on the right. As a reminder, the vascular tissue includes the xylem and phloem, which are moving water and nutrients and photosynthates respectively through the plant. The vascular tissue also includes the vascular cambium. The vascular cambium is a layer of tissue between the phloem and the xylem, and all of this has to match up so that connections can be formed between the vascular tissue of the rootstock and the scion so the plant can then function as a single unit. Wind or workers moving the plants around a nursery can cause the rootstock and scion to become misaligned, so pressure is necessary to maintain cambial alignment while the graft is taking. Some pressure may be exerted by the grafting technique that's used, cleft grafting, for example, but pressure is usually applied when the graft is made by using grafting tape or bands, as you saw in that short video at the beginning of this lecture, or sometimes clips are used for non-woody species. Tape and bands also help to reduce water loss from the wounded surfaces. In the photo here, you can see a bud graft on ginkgo that's had grafting tape applied to hold the bud in place on the rootstock. So here's the bud right there that's been grafted onto this rootstock. Polarity is important in grafting, just as we saw with cuttings. The scion must be joined to the rootstock with the proximal end downwards. The time of year at which grafting is done can be important. Grafting must be done at a time when the scion and rootstock are at an appropriate physiological stage. This can differ between species and which part of the country or even the world that you're in. It's important to prevent the scion from drying out. Until the graft is taken, the scion has no way of taking up water. When grafts are done in the field or orchard, or containerized plants are to be left outdoors, then grafting wax can be applied to the graft, as you can see in the photo on the right here. The grafting wax doesn't look particularly attractive, but it's effective. Smaller plants in containers can be placed under mist in the greenhouse or in a hoop house. Some nurseries place a plastic bag over the top of grafts in order to maintain a high level of relative humidity around the scion and the graft. The length of time needed for a graft to take depends on the species and the environmental conditions. It may take just a few weeks for a graft to take in plants such as greenhouse-grown citrus, or it can take several months. After the graft is taken, any bands, tape, or clips should be removed promptly. Some bands are now biodegradable and will fall away naturally after a specific length of time, which obviously saves quite a bit of labor. So what type of plants are grafted? Well, almost all of California's economically important tree fruit are grafted, and you can see a list of those on the right. And a really great source of information about California's important tree fruit and nut crops can be found at the UC Davis Fruit and Nut Research and Information Center. Many woody ornamentals are grafted. For example, ginkgo cultivars, many roses, many Japanese maples, dogwoods, and ornamental crabapples and cherries. An increasing number of annual edible crops are also being grafted, especially plants in the brassica, nightshade, and cucurbit families. Examples include kale, squash, watermelon, cucumber, eggplant, tomato, and peppers. The rootstocks confer resistance to soil-borne diseases such as verticillium wilt, fusarium wilt, and nematode root knot. Cacti are also sometimes grafted. It may just be to mass-produce novelty plants, such as the ones pictured on the right here, which always seem to be available at Home Depot. But some mutations of some cacti lack chlorophyll, which means they can't photosynthesize, so that means they can't be propagated by stem cuttings. The mutated section has to be grafted onto a rootstock that does have chlorophyll and will be able to provide this photosynthase for the scion that doesn't have chlorophyll. Cristate or monstrose growth forms on cacti can often be difficult to root from cuttings, so they're usually grafted. Some mammillaria species are prone to rotting when they're grown on their own roots, so these are also grafted in order to avoid problems with rotting. Grafting can also speed up the growth of very slow-growing species of cacti and encourage earlier blooming. This can be an important factor for plant breeders and in conservation. You've probably realized that grafting is labor-intensive, and therefore plants that are grafted are more expensive to produce. So why do we go to all the trouble of grafting plants? Well, there are many reasons. Firstly, it may be the only commercially viable method of propagating some varieties, such as the pink flowering form of our native tree, California buckeye. This tree normally has creamy white flowers and is propagated by seed because it doesn't root from cuttings. The only way to propagate the pink flowering form, though, is by grafting it onto seedling rootstocks. The rootstock can confer pest resistance on some grafted plants. For example, European vineyards in the 19th century were decimated by a sap-sucking insect, the phylloxera, the grape phylloxera. It was realized that the American grape, Vitis labrusca, was resistant to the insect, so many grapevines were grafted onto Vitis labrusca rootstocks. Woolly aphid, Eriosoma lanigerum in apples, can be controlled by using resistant rootstocks. And in peach, several rootstocks have been bred to provide resistance to root knot nematodes. Nemagard was introduced in the 1950s, Nemared in the 1980s, and Guardian in the 1990s. And Florida Guard was introduced for the Florida peach market. The rootstock can also be used to confer disease resistance. In the early 20th century, yields of citrus orchards in California started to fall as a result of several Phytophthora species, predominantly Phytophthora citrophthora and Phytophthora nicotianae variety parasitica. Grafting onto resistant rootstocks, such as sour orange, was a solution. Grafting citrus onto rough lemon, Citrus jambiri, or citrange, which is a hybrid between Citrus sinensis and Poncirus trifoliata rootstocks, are solutions for avoiding another citrus disease, Citrus tristeza, which killed thousands of trees in the 1930s. In apples, the M7 rootstock confers resistance to fire blight, which is a highly infectious bacterial disease caused by Owenia amylovera. It attacks many plants in the rose family, but is most economically devastating on apples and pears. The photo on the right here shows a Valencia orange, which was grafted onto sour orange rootstock that has died as a result of Citrus tristeza. Grafting techniques can also be used to overcome soil problems. For example, rhododendron normally needs acidic soils with a low pH of around 4.2 to 5.5, and it prefers to have high organic content in the soil in which it's being grown. This limits the number of ornamental landscapes in which rhododendrons can be grown successfully, and they're highly popular ornamental shrubs. The relatively recently introduced rootstock Incaro tolerates soils with a pH of up to 7.5 and also tolerates cold down to -20 degrees Celsius, which is -4 degrees Fahrenheit. It also confers tolerance of clay soils. The ornamental hybrid dogwood, Cornus Eddie's White Wonder, is grafted onto Cornus Natalii for the Pacific Northwest market, but it was found that this rootstock isn't particularly tolerant of Florida heat and humidity. So Eddie's White Wonder is grafted onto Cornus Florida rootstocks for the southeastern market in the US. We can also use grafting techniques to modify the growth habit of some plants. In the bottom right corner, you can see a photo of a standard rose. Standard roses are also sometimes referred to as tree roses because of their single main stem that's reminiscent of a tree. Standard roses are probably long past the height of their popularity, but you still see them occasionally in retail nurseries and specialty nurseries. The rootstock for standard roses is allowed to grow to at least 3 feet tall before being grafted close to the top of this stem. In recent years, several species and hybrid cultivars of the woody genus Grevillea that's native to Australia have become popular ornamentals in California. Many of these shrubs grow really wide and are way too big for many of our smaller gardens. One way around this is to graft these wider growing shrubs onto seedling rootstocks of Grevillea robusta at a height of about 3 to 4 feet. The result is a standard shrub that has a somewhat weeping habit and enables Grevillea to be grown in many of our smaller gardens. One of the most important benefits of grafting in the fruit tree sector is a reduction in tree size. Breeding work at the East Malling Research Station in the UK resulted in the introduction of several semi-dwarfing and dwarfing apple rootstocks, which limit the mature size of the tree. The M9, which was a rootstock introduced back in the 1950s, is still the most important rootstock used around the world. And the MM106 also confers resistance to crown and collar rot, as well as controlling size. Dwarfing rootstocks have enabled high-density planting that produce higher yields per acre than traditional low-density orchards. Smaller trees also mean that apples can be harvested without pickers having to use ladders, so harvest is faster, safer, and less expensive. In the 1970s, the Colt rootstock was released for cherries, and it grows to just 50% of the height of traditional rootstocks. Breeding in Germany has resulted in the Gisela rootstocks, Gisela 5 and Gisela 6. Gisela 5 grows to half the size of Colt and has enabled cherries to be grown in high tunnels in northern Europe and the northeastern US. In the photo, you can see cherries on G5 rootstocks being grown in high tunnels at McLeaf's orchard in northern Pennsylvania. This slide shows you the dwarfing effect of the various rootstocks that are available for apples. An apple tree that's grown on its own roots, so an ungrafted apple tree, will grow to around 20 feet tall. Of the 10 rootstocks that were released by East Malling in the UK, 2 are still in widespread commercial cultivation, M7 and M9, and I mentioned just a couple of minutes ago that M9 is still the most important apple rootstock in the world, despite having been released as long ago as the 1950s. Several apple rootstocks have been developed at Cornell University, and they're included in the diagram here. They have the designation G, which stands for Geneva. As you can see from this diagram, M9, which is here, limits the size of an apple tree to around 8 feet tall. Grafting also has the benefit of allowing us to repair damaged trees. Let's say, for example, you have an orchard that's been badly damaged by particularly strong winds. Instead of having to replant the damaged trees with new ones, you could just regraft them. Grafting also allows us to change the cultivar of an existing orchard. Let's say, for example, you have an orchard of Gala apples for which demand is falling because everyone wants Fuji. So instead of grubbing up the trees and replanting and starting from scratch, you can just cut back the existing trees to just below the original graft, then use a cleft graft or a bark graft that are shown in the photos here to change the orchard over to Fuji apples. In the top photo here, the graft has just been done and wax will be daubed over the surfaces to seal them. In the bottom photo, which shows a bark graft, you can see that wax has already been applied to this graft. These two grafting techniques look strange initially because there's such a mismatch in size between the rootstocks and the scions. They won't look so strange in a few years though, once the scions have grown. And let's remember that aesthetics aren't as important for commercial orchard trees as they are for ornamentals or fruit trees that will be sold in retail nurseries. The photo on the right is an example of an apple orchard in which the variety has been changed. This is an example that was reported in the Good Fruit Grower Journal in October 2018, where ridgetop orchards in western Pennsylvania has grafted over the old Red Delicious orchards that were planted on conventional spacing at 5 by 16 feet. And the photo shows a bark graft, which you also saw in the previous slide. The orchard owners regrafted with Gala and Honeycrisp and also completely changed the growing system to one where the new varieties are trained as a multi-leader system, which increases the fruiting axes per acre dramatically, without the same investment as replanting. The result of this is higher yields per acre. Grafting gives us the opportunity to try out some novelty plants for the retail market that are aimed at today's smaller gardens or even apartment balconies. Several fruit varieties can be grafted onto a single rootstock to create what are often called fruit salad or fruit cocktail trees. A similar technique can be used with tomatoes to produce a plant that produces several different varieties. On the far right here, you can see an intergeneric graft created between a tomato and a potato, which is marketed in retail nurseries and under the trade name ketchup and fries. While these novelty grafted products may not appeal to the purists among you, they've been shown to be a great way of getting kids really excited about growing veggies and fruit, and adults too, who are new to gardening. Another novelty application of grafting is Arbosculpture, which is the art of growing stems of trees by bending them, weaving them, pruning, and/or grafting. It's not unusual to see the houseplant weeping fig, Ficus benjamina, trained in this way. For us here in the Monterey Bay, perhaps the ultimate in arbosculpture are the circus trees that were created by Alex Erlandson in the 1920s in Scotts Valley. He created many arbosculpted trees, mainly with sycamore trees, Acer pseudoplatanus, that were woven and grafted into wonderful shapes. Sadly, his tree circus didn't make him any money. In the late 1990s, his trees were saved by a Santa Cruz architect, Mark Premack, and Michael Bonfanti, owner of Gilroy Gardens, and you can now see the 25 surviving trees at Gilroy Gardens. And you don't even have to pay to go into the gardens to see most of the trees, because they're all planted right at the entrance before you have to go through the ticket barrier. The uses of grafting aren't confined to the propagation of fruit trees and ornamental plants. This isn't a propagation technique, but grafting techniques are also used in the virus indexing of some plants, including strawberries. The viruses tobacco streak virus, strawberry featherleaf virus, and strawberry latent C virus are detected in strawberries using this method. The way graft indexing works is that plant pathologists use an indicator plant, which is known to be susceptible to the virus that's being tested for. On strawberries, the middle leaflet is removed from a leaf, and then a leaf from a plant that's suspected of being diseased is grafted on to the indicator plant. If, after a period of time, the indicator plant begins to show symptoms of the virus, then it's confirmation that the plant the grafted leaf came from is diseased. The grafting technique used is usually a wedge graft, which involves making a vertical cut down through the exposed petiole, then shaving two sides of the petiole of the suspect leaf to expose the vascular tissue, then inserting it into the cut or the wedge on the indicator plant. A small plastic clip is used to hold the two together. There are many grafting techniques and often several variations of each technique. Usually our last class of the semester is a really fun one where we get to practice some of the grafting techniques, and we have a demonstration from Terence Welch, who has a local organic orchard in Watsonville and is a member of the California Rare Fruit Growers Association. And I'm really sorry that we can't be doing that this year. If you're interested in learning more about grafting techniques, I really encourage you to keep an eye on the website for the Monterey Bay chapter of the California Rare Fruit Growers to see when their next event may be. There are also, of course, loads of videos on grafting on YouTube. Regardless of the grafting technique you use, it's always important that the cambium lines up. Always use a sharp, clean knife and make sure that any cut surfaces don't have any dirt on them. The cut surfaces should be smooth with no curves or bumps so that the surface of the rootstock fits closely against the surface of the scion. All the techniques require manual dexterity and patience, and it's good to practice first on wood that you have a plentiful supply of just to get the hang of the technique that you want to use. Willow is a good wood to practice on if you have any close by to where you live or work. Finally, let's talk about what the future of grafting might look like. You've seen in this lecture that grafting is more than just a propagation technique. It's used to confer pest and disease resistance, tolerance of soil physical properties, to control size, and perhaps one day we'll be able to accomplish all of this with gene modification techniques such as CRISPR instead of grafting. It's probable that the grafting of woody ornamentals will decline in the future as a result of a shortage of skilled grafters and further advances in our ability to root cuttings of hard-to-root cultivars, or by advances in tissue culture. This may result in a reduction or closure of nurseries that grow grafted woody species, and in a continued consolidation of larger nurseries. But perhaps there will also be opportunities for small niche market nurseries to continue producing small quantities of specialist or regionally appropriate plants using conventional grafting techniques. It's likely that new rootstocks will be developed in the relatively near future that will further expand certain crops' tolerances of particular soil or environmental characteristics. Drought tolerance, for example, which will enable growers to adapt to climate change and also enable marginal land to be productive or even to be brought into production. An increased number of annual vegetable species are also likely to be grafted. The increasing number of grafted veggie annuals will result in more and more automation of grafting, as it just isn't economically viable for huge numbers of field crops to be grafted by hand. Robotic grafting technology is already in use in Europe, and will see increased adoption of the technology in the USA. In the photo here, you can see robotic tomato grafters in the Netherlands that are being produced by the ISO group. Similar technology is being developed that will work with some of the easier to graft woody species, such as citrus. Here's a quick summary of what's been covered in this last unit. Grafting is more than just a propagation technique. It's also used to confer pest and disease resistance, tolerance of soil physical properties, to control size, for virus indexing, and to create artistic arbosculptures. Historically, grafting has been used predominantly on woody fruit and nut trees and ornamental trees, but it's increasingly being used for some annual vegetable crops. Grafting requires a high level of manual dexterity and it's labor intensive, and this adds to the production costs of grafted plants. In the future, grafting of some plants is likely to be replaced by advances in other propagation techniques, such as tissue culture. It's also likely that many grafting procedures will be automated. Thanks for listening. That's the end of this unit. Now head back to Canvas to take a short quiz on grafting.